This is an AS Further Mechanics 2 question on circular motion. A car moves round a bend which is banked at a constant angle of theta to the horizontal. When the car is travelling at a constant speed of 80 km per hour, there is no sideways frictional force on the car. The car is modelled as a particle moving in a horizontal circle of radius 500 meters. Part A, find the value of theta. Well, the first thing you want to do is draw a diagram indicating what's going on here. So here's my road, which is banked at the angle here of theta. I'm going to represent the car by this block here. I don't know the mass of the car, so I'm just going to call that M, which means I can put the weight in, and the weight's going to be acting vertically downwards. That's going to be mg. There's going to be a normal reaction, which is a normal to the slope of r. And in circular motion, our acceleration acts horizontally towards the center of the circle, A, which will be equal to v squared over r. Now, the first thing I note is that v is given in kilometers per hour, and I need to convert that kilometers per hour to meters per second. So let's do that first. 80 kilometers per hour. Well, we need to convert the kilometers into meters by timesing it by 1,000. So that'll give me how many kilometers in an hour. I want to know how many meters in an hour. I want to know how many meters in a second. So I need to divide by 3,600. And that gives me 200 over 9. I'm not going to round it because I'll need to use this in subsequent working. So 200 over 9 meters per second. So that's going to be my value of V. R is going to be the radius of the circle. That's already given in meters, so R is 500. And I'm going to be resolving horizontally and vertically. So I want to write down what the horizontal and vertical components of the normal reaction are. Now this angle theta is going to be the same angle that's here, so we'll mark that on as theta, and so that will give me r cos theta, which is going vertically, and then up here horizontally r sine theta. So we'll start by resolving vertically. So if I do that, I will get r cos theta is equal to mg. This is my first equation. Then I resolve horizontally. Now there's only one force acting on the car, and that's going to be this r sine theta. So that will be equal to ma. So using F is equal to ma horizontally, what I will have is r sine theta is equal to m, my m, times by a, and that's going to be v squared over r. Now I have v and I have r, so r sine theta is equal to m times by v squared, so that's going to be 200 over 9 squared, divided by the radius 500. So working that bit out, I will have r sine theta is equal to 80 over 81 m. So I can take my two equations here, they are sine theta, they are cos theta. I can divide one by the other to find tan theta. So let me write it out in full first. So I'll have r sine theta over r cos theta is going to be equal to 80 over 81 m over mg. So my m's are going to cancel out, the r's are going to cancel out, and sine over cos becomes tan. So I'll get tan theta is equal to 80 over 81, all divided by g, So I can do the tan inverse of that to get the value of theta, and let's see what we get. So the full answer for theta from my calculator, 5.75487 and so on. I need to give an answer to either 2 or 3 significant figures, so I can give 5.75, that's 3 significant figures, or to 2 significant figures I'd give an answer of 5.8, and that's in degrees. So remember, use of G, round to 2 or 3 significant figures. Part B, what we want to do is to identify one limitation of this model. Okay, so you can pick any one of these limitations that I've written here. So the first one that I've got is that all the weight of the car is acting at a single point. That's where we put our mg going down. Because we've got the weight of the car all acted at a single point, and that point is on the road, that means that we've got the center of mass of the car on the road. Now, in reality, that wouldn't be true. It would be somewhere above the road, but cars are made so that the center of mass is low enough that they don't topple over, but it wouldn't actually be on the road. And the third one that I've got here is that we've got the car only in contact with the road at a single point, that same point where we've put the mg, whereas in reality cars are going to be in contact with a road with at least 4 points. That's going to be the 4 tires if it's a 4-wheeled car. Okay, the speed of the car is increased so that it is now traveling at a constant speed of 90 kilometers per hour. Now remember, in the previous part, in part A, that speed was 80 kilometers per hour, so it's now going faster. The car is still modeled as a particle traveling in a horizontal circle of radius 500 meters. Part C, describe the extra force that will now be acting on the car, stating the direction of this force. Now, because v is increased, that means the acceleration will increase. That's v squared over r. And because that's increased, to maintain balance, I'll show you what that looks like in a diagram in a moment, we will now have to have friction, which will be acting down the slope. So just a little diagram to explain what's going on here. So here's my banked road with my car. Here we've got the mg going down. We've got r pointing as a normal to the slope. We have our acceleration, which is now larger, v squared over r. And at the moment, we have this component of the normal reaction. Let's do that over here, which is the r sine theta. And that was equal to the acceleration before, but now this is increased. So to help this along, what we need is some friction, and that frictional force, I guess, which we can call mu r, will be pointing in this direction here. So F is equal to mu r, and then I've got this additional force to keep the balance between the r sine theta and the acceleration. And part of that frictional force, that mu r, will be acting horizontally, and part of it will be acting vertically down here, which will then get added to the mg